Welcome everyone. In this video, we are going to prove that if the square of a number is odd, then the number is odd. If the square is even, then the number is even. So how do we start? And why do we do this? Well, in a previous video, we already proved that if x is even, so if x, which is just an integer, if x is even, then we conclude x squared is even. And as we proved, this also holds for the odd case. And you can access this proof from the cards right now, also from the descriptions part. Now, what we want to do today is to show that we can go the other way. So we want to prove the converse of the statement that we derived a couple of videos ago. And the whole goal of doing these two is to prove that the square root of 2 is irrational. In that proof, we will use these two facts, and that video is coming in the future, hopefully, in the near future. So how can we start? Well, the way I want to start is first with the even case. So if we have the knowledge that x squared is even. So let me separate this part. This was recap and foreshadowing. Now we start the derivation. We are given that x squared is even. And we're also given that x is an integer. It is an element of the integers. So x squared is also an element of the integers. If you square an integer, any integer, positive or negative, you will get an integer. If we know that x squared is even, then we can represent it like this. X squared is equal to 2 times a factor k, and k here is just another integer. We have all the integers. We have 3 integers right now. X squared, and k. Okay? So, if I take the square root of both sides, on the left, what do I get? I get the square root of x squared. And on the right, I get the square root of 2k, Well, what is the left? It is x? No, it is not x. What if x is negative? Yes, if it is negative, then this doesn't hold because the square root should give a positive value. So to avoid that pitfall, we put a plus or minus. Okay, this basically gives the absolute value of x, which is just plus or minus x. Then this is equal to, on the right, I will separate this one square root into 2 parts. We will have the square root of 2 times the square root of k. And here, notice one thing. Since we know x is an integer, that's how we choose x, we were able to conclude that x squared is also an integer. That means this right side should be an integer because it is equal to x. We have the square root of 2. Right now, we don't know whether or not it is irrational because we didn't prove it yet. We will prove it in the future, but we didn't prove it yet. However, we know that it is not an integer. Even if it is irrational, which it is not, but even if it is, it still isn't an integer. And if it is not an integer, well then, this does not hold, okay? Because you can't multiply an integer, you can't multiply something that is not an integer with another thing to get an integer. But you can do it by this. If you have something that is not an integer, you should multiply with something that is still not an integer. I said it wrong, I guess, a minute ago. So what I'm trying to get at is that inside this k, we need to have a hidden 2. So that, and also we have an n perhaps, and n, surprisingly, is another integer. Wow, what a surprise. Inside that k, we have a hidden 2 factor. And when we take it out, we will have 2 times the square root of n. Because we have the square root of 2, another one here, we get 2. And here the square root of n should also be an integer. And it will be an integer because x is an integer. But we don't worry about that. We don't care about it. All we care about is this 2 factor here. Because if we have a 2 times another integer, well, we get n actually, even number. So we can conclude from this that x is even. So again, what was the key point here? Well, the key point here was we said x squared should be an integer. So if x squared is an integer, we represent it like this. And we know that x is an integer. We defined it like that. And we saw the square root of 2 here. We said, hey, we don't want square root of 2. It can't be an integer. We need another square root of 2 so that they will cancel each other, give us 2. And when we have 2, we have an even number. I hope this part makes sense. And if it does, great, because this was half of the job. Now comes the second half. Now we want to show that we want to consider the case actually that where x squared is odd. And I am not going to write what I just written. Oh, actually, no, what? Let's write them. So here x is still an integer and consequently x squared is an integer. So if x squared is odd, how can I represent it? Well, it should be in the form of x squared is equal to 2k plus 1, where k is again an element of the integers. Here I want to mention one thing. I will start with a different approach. On the last derivation, here on this page, we took the square root of both sides. But that's not how I want to do it. I mean, I guess you could do it like that, but I have another approach. I want to consider x this time, directly x. I will have two cases, case 1 and case 2. First case will be where x is equal to 2n. And n is an integer, again, surprise, surprise. So in this case, I consider that x is an even number. And in the second case, I consider that x is an odd number. I will start with these two ideas and I will square them and then I will see whether or not I can get a form 2k plus 1. If I can, well, great, then I have shown if x squared is odd, then x should also be odd. If I don't, for example, if I get it from case 1, well then that is not the case. So let's get started. If I square both sides, I get x squared is equal to 4n squared. And here, whatever we have for n, it doesn't matter. We multiply it by 4 so that we get something even here. And if it is even, well then x squared cannot be odd, so it is not in the form 2k plus 1. So from this I see that x squared is not equal to 2k plus 1. Alright, now what about case 2? For case 2, I square both sides and I get 4n squared plus 4n plus 1. And you can check that this in fact works by multiplying out yourself, or you simply know this by heart. So if I here define my n, if I make this 2k, you will see that I will have a plus 1 and consequently this will be in the form 2k plus 1. And I can define 4n squared plus 4n as 2k because look at this. I have 4n squared plus 4n. If I make this 2k, well then 2's cancel. This becomes 2. I have 2n squared plus n is equal to k. This totally makes sense because I have an integer. I have its square, which is also an integer. So I add them, I get an integer. I multiply it by 2, I can still get an integer. This works out. I can really substitute 2k for 4n squared plus 4n. So this is fine. And as we noticed, we get something that is in the form of 2k plus 1. So for case 2, it holds that x squared is equal to 2k plus 1. And then we showed it. We showed that if x squared is odd, then we can conclude that x should also be odd, because when we consider the two cases, and there are only two possible cases, a number is either odd or even. If the number is an integer, we consider the two cases, and we show that for the even case, for this one, it doesn't work out. Only for the odd case, it works out. So what did we have? Well, we were able to, on this page, we were able to show, and let's write it here, if x squared is even, then x is even. And lastly, on the last page, we showed that if x squared is odd, then x is odd. from the last video, from one of the last videos, we also have this result. So we now know that we can go both directions, which means if we combine them on a new page, we get a very powerful and something that is also intuitive. We get that if x is even or odd, then we have a two-way path. We can go both directions and we can conclude that x squared is even or odd. So if x is even, x squared is even. If x squared is even, then x is even. Okay, and it works for odd as well. This is a biconditional. So it means that if you know that the one on the left is correct, then you know the right is also correct. If you know the right is correct, then you know the left is correct as well. And if either of them is wrong, then you can conclude that the other one must be wrong as well. And this symbol is read as if and only if. In the future, I plan to make a video about logic. This is something that is very important in the logic part of math. And I really want to make a series about that. And also, as I said, whole point of this video and the one previous was to prove that the square root of 2 is irrational. And we will use this result in that video, so stay tuned for it. This is it for this video. If you have any questions, please drop them in the comment section. I hope to see you in another video. Until then, take care.